I would like to thank the opportunity to take the opportunity to thank our speaker today, Susanne Mertens from the Max Planck Institute for Physics and the Technical University Munich. She's going to be talking about neutrino mass and sterile neutrinos and beta decays. But before we start the talk, let me briefly introduce her. She studied physics at KIT from 2002 to 2008 and obtained a master's degree in theoretical physics. And then from 2008 to 2012, did her PhD on the Katrin experiment. From 2012 to 2016, she worked as a postdoc at Lawrence Berkeley National Laboratory on neutrinoless double beta decay with the Majorana experiment, and started the Tristan project, which is an extension of Katrin to search for sterile neutrinos, and she'll be talking about that today. Since 2016, she's a Max Planck research group leader and Technical University Munich tenure track professor with a main focus on the Katrin and Tristan projects. And she pursues other activities related to Legend and IAXO, which maybe you'll tell us about, and we'll see. So thank you very much for being our speaker today. And with that, I would like to hand over to you, and we're very much looking forward to your presentation.
Okay, thank you, Christian, for the nice introduction. I hope you can all hear me well. And I would also like to welcome you to my talk on the Katrin and Tristan projects, essentially. So the neutrino mass is certainly one of the most topical open questions in astroparticle physics today. And this is nicely illustrated in this graph here, which shows that the neutrino mass is at least 5 orders of magnitudes smaller than the mass of all the other matter particles in the standard model. And this huge gap in the mass of the neutrino and the other particles makes the neutrino so interesting. So it may point to some completely new mass creation mechanism, to some completely new origin of the neutrino mass, which may be the portal to some physics beyond the standard model. But of course, at the same time, this huge difference in mass also makes the experimental determination of this value extremely challenging. And currently, there are essentially 3 ways how we can assess the absolute neutrino mass scale. So you probably know that in neutrino oscillations, which prove that the neutrino must have a mass, only the mass differences of the 3 neutrino types can be measured. But the neutrino oscillations don't tell us what is the absolute mass scale. So to assess this value, we have the option of looking into cosmology. And this is an extremely powerful technique. Here we use the fact that the neutrino is the most abundant matter particle in the universe. And even if it has a small mass, it has quite an impact on the structure formation in the universe. So by observing essentially the matter distribution in our universe with various means, we can reassess the value of the neutrino mass. And these methods are extremely powerful. They set the best limits today, and new measurements are upcoming with a good chance to actually see the value of the neutrino mass. However, whatever is deduced from cosmology will rely on a cosmological model. So it's not fully model independent. So to have an independent measurement of the neutrino mass, I think it is inevitable to also perform a laboratory-based measurement of the neutrino mass. In this case, we could take the value obtained in the laboratory and actually plug it back into the cosmological observations to make them less model dependent. And here for the laboratory-based experiments, we have the search for neutrinoless double beta decay. This again is an extremely powerful technique to learn about the neutrino mass, but it's still somewhat indirect. So here we measure the half-life of the decay if, well, we try to discover this decay and would then measure the half-life. And from the half-life, we can deduce back the neutrino mass. However, again here, we are relying on a model that describes the underlying process that mediates this neutrinoless double beta decay. So the least model-dependent approach is based only on the kinematics of a single beta decay. And as you will see, this is extremely challenging, but it provides the most direct information about the absolute neutrinos. And this last approach to assess neutrino mass is the subject of this presentation. So the general idea here, give me 1 second, I have to move the Zoom window a bit. So the general idea of a kinematic determination of the neutrino mass is to consider a single beta decay. And here, the electron and the neutrino that are emitted in the decay, they statistically share the released energy, and the neutrino mass manifests itself as a very small shape distortion in the beta decay spectrum close to the endpoint. So you can see that here in the zoom, you see that a neutrino with a mass of 1 eV would steal some energy from the electron and would reduce the maximal energy and lead to this small distortion in the shape. So the actual neutrino mass that we are measuring in this decay is an effective mass. It's the so-called incoherent sum of the 3 neutrino mass eigenstates, as in this decay an electron neutrino flavor is emitted, but we are not sensitive to the individual mass eigenstates, so we are essentially measuring the weighted average of the 3 neutrino mass eigenstates. A very suitable isotope to perform such a measurement is tritium. Tritium performs a super allowed beta decay with a rather short half-life, and a short half-life is useful since we obtain a lot of beta decays for not so much tritium. And you can imagine it's not so easy to handle large amounts of tritium, so it's preferable to have short half-lives. And also the endpoint is not too high, which makes the technical realization, as you will see, feasible. The challenge of measuring this small distortion close to the endpoint is largely related to the fact that only a tiny, tiny fraction of all beta decays actually produce an electron close to the endpoint, which therefore carries information about the neutrino mass. So that means that you need an ultra strong beta decaying source. You need on the order of 10 to the 11 decays per second. At the same time, your experiment has to have a very low background. If you imagine there would be a background level that would cover this very small, very low rate endpoint region, you would not be sensitive to the signature of the neutrino mass. And your experiment has to have an excellent energy resolution on the electron volt scale. You can see here the signature of the neutrino mass only extends over a few electron volts. And of course, since we are looking for a very small distortion of the shape, we also have to have a precise understanding of the spectrum in order to not have some systematic effect that would, for example, fake the signature of a neutrino. So where do we stand with this direct neutrino mass measurements? This is shown in the best way by illustrating this effective mass that we are sensitive to as a function of the lightest neutrino mass eigenstate. And you will see in a second why it's useful to display it in this way. So the current limit, the limits actually before the new limits that I will present in this talk, they came from the Mainz and the Troitsk experiment, and they were at 2 electron volts. The ongoing experiments, including the Catherine experiment, they are pushing this sensitivity for the first time to the sub-electron volt regime. And they are targeting a sensitivity at 200 milli-electron volt. And this is kind of a magical boundary because it allows to discriminate between the so-called degenerate mass regime, where the mass splitting between the 3 neutrino mass eigenstates doesn't play a role because the lightest mass eigenstate is so heavy. So we call that the degenerate regime. And the hierarchical regime, where the lightest mass is so light that actually the mass splittings begin to matter. And discriminating between these two scenarios will in turn help us to learn about the origin, the mass creation mechanism of the neutrino. Now, of course, physics is not over at this point, but there are already new ideas explored to go beyond that and to push this sensitivity even further. And the goal here would be to push so low that we can then discriminate the two possible neutrino mass orderings. That means whether nu1 is the lightest neutrino mass eigenstate or nu3. And this is, again, one of the big open questions in neutrino physics. So at the forefront of the ongoing experiments is the Karlsruhe tritium neutrino experiment. And this is a very old picture, but I think it's still extremely impressive. This is in 2006 when the spectrometer of the Catherine experiment arrived in Karlsruhe and drove here through the streets, and you can see, yeah, you get a good impression of the size of this instrument. So Catherine is situated at the KIT, and it's an international collaboration with about 150 members from all over the world. There are quite some groups from the US, from France, and so on and so forth. And the goal of the Catherine experiment is to reach a sensitivity at the level of 0.2 electron volt at 90% confidence level after about 1,000 days of measurement time. So altogether, this whole measurement will take about 5 years to accumulate this amount of data. So how does Catherine work? Catherine is actually not only this big spectrometer that you see on the famous picture, but it's an instrument that is altogether 70 meters long. And you can see here a person to get some impression of the size of the whole beamline. And it starts here with the so-called windowless gaseous tritium source. And here, molecular tritium in its gaseous form is inserted into the beamline, and it distributes here to the left and to the right, and is then pumped out again and is inserted again. So it's a closed loop of a molecular tritium. And with about 50 micrograms of tritium at all times in this beam tube, we achieve 10 to the 11 decays per second. So that's quite a large number. So all the electrons that are created in this decay are then guided out of the tritium source towards the spectrometer. And this is achieved with a system of superconducting magnets. So the electrons feel the magnetic field and are guided here along the beamline. Since the source is a windowless source, that means there is no wall that would protect tritium to go into the spectrometer. So instead of a window, we have a very efficient and sophisticated pumping section, which is based on differential and cryogenic pumping. And this reduces the tritium flow by 14 orders of magnitudes here from the source section to the spectrometer section. So essentially all tritium is removed in this part of the experiment. In the spectrometer, there is no more tritium, and we have an ultra high vacuum of 10 to the 11 millibars. Here in the spectrometer, this is kind of the heart of the experiment, we analyze the energy of the electrons. And you can essentially think of the spectrometer as an electrostatic filter that only allows electrons above a certain threshold to be transmitted through the spectrometer, re-accelerated here on this side, and reaching here the exit. In addition to the electrostatic filter, we have a complicated system of or magnetic field configuration. And this magnetic field configuration consists of a high magnetic field here and a low magnetic field in the center. And this magnetic field gradient aligns the electron momenta as depicted here in this with these arrows. So all electrons, the transversal energy of the electrons is converted into longitudinal energy, which is then analyzed by the electrostatic filter. So the combination of electrostatic filter and this magnetic collimation is called the Mach-E filter principle, and it allows for this extremely good energy resolution and at the same time for a very high angular acceptance. So we can increase our count rate or our statistics by combining the system, the magnetic and electric field in this way. So finally, how do we obtain the shape of the tritium spectrum? This we do with a focal plane detector here at the exit of the experiment, and we simply count how many electrons arrive at the detector as a function of the electrostatic filter potential. So here you can see a display of that. So here is the count rate as a function of the retarding energy. That's how we call, that's the voltage the spectrometer sits on. So that means the electrostatic filter voltage, and we measure the count rate as a function of this retarding energy. That means we measure a precise integral spectrum of the tritium spectrum down to about 40 electron volts below the endpoint. And then by comparing these data points with a model, we can infer the neutrino mass. So what is essential for CATRIN is a precise understanding of what we measure, as I mentioned in the beginning. And therefore, CATRIN is equipped with a large number of calibration and monitoring devices. And one of them is the high intensity electron gun. So here we have an electron gun that shoots electrons through the entire beam line all the way to the detector. And by measuring the transmission probability as a function of their energy above the electrostatic filter voltage, we can, for example, deduce the amount of gas which is present in the source. And this we can easily understand. The more gas we have in the source, the more likely it is for the electrons to scatter and lose energy, and therefore not be able anymore to overcome the electrostatic filter. And this you can see here. So for different gas densities here given by the so-called column density, you see that less electrons, the more gas we have, the less electrons make it to the detector. So by measuring this plateau here, we can deduce the absolute amount of gas in our source. And this is an important calibration measurement that's repeated on a regular basis. We can also operate the E-gun in a time-of-flight mode, and this is quite complicated, but this allows for essentially a differential measurement, and we can measure the distribution of energy lost in the scattering process. And this again is an important input for our model. The other key calibration source is the krypton, gaseous krypton source. And gaseous krypton, when it decays, it emits conversion electrons. And these conversion electrons are monoenergetic electrons just in the kilo electron volt range where we are interested in. So we use the krypton source in its gaseous form, and we just insert it into the windowless gaseous tritium source, and we do that before actually inserting tritium. So there is krypton only, and by measuring then the position of the line and also the width of the line, we can deduce back the potential and the electric potential and the magnetic field in our spectrometer, in the center of the spectrometer, which we call the analyzing plane. When we use the krypton source in combination with tritium, which is also possible, so now the source is filled with tritium, and we additionally insert krypton, then we can measure we can characterize our source. The important point here is that the source filled with tritium actually depicts a cold magnetized plasma. So we have a large number of ions and low energy electrons in our source, and together with the magnetic field, this forms a plasma that can actually exhibit some electric potential variation in the source. So again, by using krypton, we can measure the broadening of a very narrow krypton line. And this broadening tells us, or we can deduce from that, the electric potential variation in our source. So again, this is one of the most important calibration measurements in CATRIN. In addition to that, CATRIN is equipped with various monitoring devices, and I cannot list all of them, but here are the most important ones. Here in the beginning, we have the laser Raman system, which monitors the tritium purity and the exact gas composition at the 0.1% level. Here in this transport section, we have the so-called forward beam monitor, and that directly monitors the activity of the source, so the number of beta electrons, also at the 0.1% level. And here at the spectrometer, which sits on high voltage to create this electrostatic filter, we have a quite impressive high voltage divider and measurement system that allows us to determine the high voltage at the ppm level. So at 20 millivolt for an 18 kilovolt potential. So all of this was put together over the last 18 years, in fact. So the idea of CATRIN was born in 2001, and it took quite a long time to set up this rather complicated instrument. But since 2018, CATRIN is taking data. And you can see here an overview of our data taking campaigns almost up to today. It all started here in 2018 with the so-called first tritium campaign, and this led to the official inauguration of the experiment. Maybe you have seen this picture where some people were allowed to press the red button to essentially switch on the experiment. And in this, it was not only a PR event, but we also took very nice data, and we could demonstrate the stability of the overall system. Here you can see on the European Physics Journal, one of our first spectra was shown. Following this first tritium campaign, our first neutrino mass measurement happened. And this, I will explain you a little bit in more detail how this actually works. So here we measured for 22 days, and the gas density was at 22%. The reason why it wasn't at 100% is that there is always some sort of burn-in period when the system is for the first time exposed to radioactive gas. Then there are some exchange reactions with the wall, and you cannot immediately go to 100%. But you will see in the second campaign, we were able to ramp up this gas density. The purity of the gas was extremely high, almost 100% of tritium, and this leads to this activity 10 to the 10 becquerel, so already quite a high statistics. With these 22 days, we collected 2 million of beta electrons in our region of interest. And how did we actually measure the tritium spectrum in this first neutrino mass campaign? So the tritium spectrum was measured by measuring the count rate in a region from minus 40 electron volt below the endpoint and 50 electron volt above the endpoint at 27 different high voltage set points. And you can see here in this lower graph these 27 set points and how much time we spent at each of these set points. And you can see here we measure very fine-grained and most of the time, and this is where we are. This is the region where we are the most sensitive to the neutrino mass. We spend quite some time also above the endpoint, and this is because we need a precise determination of our background. To go through these 27 high voltage set points just once takes 2 hours, and then we repeat the measurement at these 27 high voltage set points 274 times by going up and down with the high voltage. And thanks to the very good high voltage stability and also reproducibility, we can eventually stack all these 274 spectra together to observe or to obtain one very high statistics integral tritium spectrum that we then compare with our model prediction. And yeah, to do this fit to our model, we need, of course, a precise integral tritium spectrum calculation. And this is quite involved in the case of the Catherine experiment. And essentially, we need two ingredients to describe our integral tritium spectrum. The first ingredient is the differential tritium spectrum, which is essentially given by Fermi's theory, but there are various corrections to that. So we have to, most importantly, consider that we are not using atomic tritium, but molecular tritium. And with that, we have to consider the molecular final states. There are also corrections due to the Doppler broadening, due to the finite velocity of the tritium molecules in the source. And then there are some theoretical corrections like radiative corrections. On the other side, we have the description of our experiment, which is given by the so-called response function. And this function here describes the spectrometer resolution. This is this sharp increase in the beginning, and it encodes the information about any energy loss that can happen in the experimental setup. So energy losses due to scattering or synchrotron radiation, etc. So by performing a convolution of the differential spectrum with the response function, we then obtain our prediction for the integral spectrum. And eventually, we fit this prediction to our data by allowing not only for the neutrino mass as free parameter, but for 4 free parameters. In our measurement, the absolute the amplitude, the normalization of the spectrum is a free parameter. The offset in x direction, which is essentially the effective endpoint of the spectrum, is a free parameter. We have a constant background level here above the endpoint. And of course, the neutrino mass, which appears as neutrino mass squared in our model, is the most important free parameter. So before going ahead and fitting this prediction to our data, we actually perform a threefold blinded analysis in order to not bias ourselves after having seen the data. So the first step is that we freeze the entire analysis and all analysis cuts and strategies on a Monte Carlo copy of the data. So we reproduce all the runs given all the slow control parameters in the computer, and we tune our analysis on this Monte Carlo copy of the data. When we are satisfied with that, we turn to the true data, but still here we use a blinded model, and we blind our model by modifying the molecular final state distribution with an unknown broadening in the final state distribution. And finally, the last step in the blinding procedure is that we perform the entire analysis with 2 completely independent analysis strategies. And they differ mostly in the way that systematic uncertainties are treated. And I will not go into the technical details, you can ask me later. On the one hand, we have the covariance matrix approach, and on the other hand, we have the Monte Carlo propagation of systematic uncertainties. And so these 2 techniques were developed for the first neutrino mass measurement. So which are these systematic uncertainties for this first measurement? Here I give you an overview. So the first systematics arises from our description of the molecular final states. Then we have some systematic uncertainties related to the scattering. So there are uncertainties in the column density and in the energy loss function. The magnetic fields are only known to a certain precision. And most important for this first measurement are the background characteristics. So our background can in fact have a certain time correlation, so time dependence. And the background may have a very small dependence on the retarding potential or on the electrostatic filter voltage, which leads to some sort of background slope or background shape. And then finally, we assign a small uncertainties due to the way that we combine our data. So looking at the breakdown of all these systematics, you can see that for this first measurement, we are largely dominated by the statistical error. It was only a short measurement, and you can see that all these systematic effects are not yet relevant for this very first campaign, but of course they will become very relevant in the future. The dominant effect here was the so-called non-Personian background, and this is exactly related to this time dependence of background. The origin of this are actually radon decays that occur in the large volume of the spectrometer. And in these radon decays, a large number of secondary electrons can be created that arrive on our detector in a short period of time. So in this way, we have background events that are not Personian distributed at our detector, but that arrive in extended bursts on our detector, leading to this non-Personian over-dispersion of our rate. So this is essentially an additional statistical uncertainty in our measurement. We are very happy that this effect is actually completely removed since we improved our radon retention system and also the electromagnetic configuration to remove this background completely. Okay, so now let's have a look at the actual data. Now here you can see our final fit result and the data including the full statistics of 2 million of electrons. Now we perform the fit with the 4 free parameters: background, signal normalization, effective endpoint, and neutrino mass squared. And the first thing that you can see here in the graph nicely is that we have a very beautiful agreement of our model with the data. With you can see it here in the residuals. So the goodness of it is at 56%. And it's also astonishing a little bit is that maybe you wonder where are the error bars in this graph, and they are not missing, they are just so small. And we have to multiply the error bar with a factor of 50 to make them visible in this graph. So that gives you maybe a small impression of the precision that Katrin will reach. So already with this very first data set, which is super statistics dominated, already the error bars are tiny. So now what is the best fit result? This is displayed here in this graph that shows the best fit result for the neutrino mass and the effective endpoint. And for the neutrino mass squared, we find as a best fit -1, +0.9, -1.1. And this is very much compatible with 0. So the probability to measure this value is 16% if the truth was that the neutrino mass is 0. So this is completely compatible with a statistical fluctuation. For the endpoint, we measure this value, and this is not directly the Q value of the decay. So we have to take into account the potential in the source and also the work function of the spectrometer to convert that to a Q value. And if we do so, we can compare with literature values. And also here we find a very nice agreement, which gives us some confidence that we understand the apparatus. So from measuring, from having this best fit result here, which means that we do not see the effect of a neutrino mass, we can set an improved upper limit on the neutrino mass. And the official upper limit that was published in the PRL is based on the so-called Lokov-Chachov method, which essentially quotes the sensitivity of the experiment in case that the best fit result is negative. So that's a conservative approach and is the official limit of Katrin. So this improves the previous limits by a factor of 2. If we use the more well-known Feldman-Cousins technique, in that case, we get a little bonus from having a best fit result in the negative regime. This is displayed in this belt construction that some of you may be familiar with. So if the best fit result is negative, then actually the limit that you can set is slightly improved. And so this effect is switched off in the Lukov-Chakov method. So in that case, we would have a limit at 0.8. We also performed a Bayesian method to retrieve an upper limit. This was done with the BAT framework, which was developed at the Max Planck Institute. And here, what is elegant about this is that you can set a prior on the neutrino mass. So this is one way to overcome this issue of how to handle negative neutrino masses. So in the Bayesian case, you can actually demand that the neutrino mass squared is positive. And in this case, we obtain a very comparable limit to the other cases. Putting all of that in the historical context, you can see here the entire history of direct neutrino mass measurements, and here zoom into the Mainz and the Troitsk and the first result from Katrin. And you can see that with this effective 5 days of data taking, we have already improved the statistical error by a factor of 2 and the systematic error by a factor of 6 with respect to Mainz and Troitsk, which were experiments that ran for several years. Okay, so that's impressive, but it is of course only the very start. So we have to improve a lot. We have to measure much longer and still improve the systematic uncertainties to reach our final goal. So how does it continue? After this first campaign, we performed a second campaign. And in this case, the column density was already at almost 100%. So this burn-in period was over at that point. In this campaign, which lasted about 1 month, we doubled our statistics, so an additional 4 million of electrons. And based on a sensitivity consideration, we have now, for the first time, the sub-EV sensitivity of 0.7 electron volts. The data unblinding of this data set is ongoing just right at this moment, and we hope to release the results of this data set in the very near future. Following this second campaign, there was a period where we still performed some improvements on the apparatus. And most importantly, we introduced a new electromagnetic field configuration. And here the idea is displayed. So the background in Katrin is the most limiting factor at the moment. The background is too high. It's about a factor of 20 too high with respect to the design report. And the background in Katrin originates from the volume of the spectrometer. So electrons are created here in the volume, and if they are on the right-hand side of the maximum potential, they are accelerated to the detector. So by shifting the maximum potential towards the detector, we essentially reduce the volume which is projected onto the detector, and thereby reduce the background. So in this configuration, which we call the shifted analyzing plane, we can reduce the background by a factor of 2 to about 150 millicounts per second. And this, of course, helps a lot for the future measurements. After these improvements, we started running again since summer this year, and the system is currently taking data stably. And with the upcoming 1,000 days of data taking, we will then tackle the 0.2 or the low sub-EV region with the full data set. And as I said, we hope to release a new result actually not only after 1,000 days, but maybe beginning of next year. So with this, I would like to switch gear a little bit, and maybe I'm a little bit too slow, but let's see how far I get. And I would like to speak a little bit about sterile neutrinos. So if you look at the standard model of particle physics, you notice that all particles appear both left and right-handed, but only the neutrino is missing its right-handed partner. And this stems historically from the fact that the neutrino was assumed to be massless in the standard model. But since the discovery of the neutrino oscillations, we know neutrino has a mass, and the most straightforward way to introduce neutrino mass is to allow for a right-handed partner of the neutrino, because in that case, we would allow the neutrino to take part in the interaction with the Higgs field. So by doing so, by introducing a right-handed partner, we automatically introduce new neutrino mass eigenstates. And the mass of these new mass eigenstates is completely arbitrary. There is not much guidance from theory. For the case of sterile neutrino search in beta decays, two of these mass scales are very interesting. And these are the electron volt and the kilo electron volt mass scale. And I will not go much into the details of the motivation of these, but I would just like to remind you that the light sterile neutrinos, they are motivated by some long-standing anomalies in neutrino oscillation experiments. So here, this is shown here. So various detectors that were placed in a close vicinity to a reactor measured a deficit of a neutrino flux compared to the prediction. And this deficit could possibly be explained by the existence of a fourth neutrino mass eigenstate, a so-called sterile neutrino. The KeV scale sterile neutrinos are interesting because they are a viable dark matter candidate. And they are especially interesting because they could be warm dark matter, which would mediate some tensions that exist in purely cold dark matter scenarios when we look at the exact structure distribution. So both of these sterile neutrino types leave a signature in beta decay. How does this happen? So if we consider again the beta decay, we see that here a flavor eigenstate is emitted, and this flavor eigenstate is a superposition of the various mass eigenstates. So now if we would have a heavy mass eigenstate mixing into the electron flavor, we would have correspondingly a beta decay branch, which endpoint is reduced by the mass of this heavy sterile neutrino. And the amplitude of this additional decay branch would be given by the mixing angle, meaning by how much of this fourth mass eigenstate is mixing into the electron flavor. So since we observe a superposition of the active and the sterile branch, we get here this characteristic distortion of the spectrum. And this is the signature of the sterile neutrino that we can look for. And for the case of the light sterile neutrino, you see that this signature appears, let's say, 10 electron volt below the endpoint. And with the current Catherine data, we have already measured the spectrum down to 40 electron volt below the endpoint. So essentially, we can use this data set to perform a sterile neutrino search. And this is exactly what we did. We used the same data set as for the neutrino mass, but we added one additional neutrino, a sterile neutrino, in our model. And then we performed a standard grid search in the relevant parameters, the mass and the mixing angle of the sterile neutrino. And in the last step, we translate that to the parameters that are typically used in oscillation experiments in order to compare our results. And you can see in this graph here already that the strength of a search in beta decays is this very high signal to background ratio once you go further away from the endpoint. So here at 40 electron volt below the endpoint, we already have a signal to background ratio of 70, which is much superior with respect to, let's say, reactor experiments or oscillation experiments. And here you can see the result. So what you can see here, first of all, we do not observe a signal from a sterile neutrino, so we set an exclusion limit, and this is shown here in blue. And you can see that in the high delta M region, we improve with respect to the existing limits from the leading oscillation-based experiments, the DANS, Prospect, and Stereo. They are shown here. And also, we start probing parameter space that is preferred to explain this so-called the reactor anomaly that I mentioned before. In the low delta M region, you can see that we improve with respect to the Mainz and the Troitsk limit. And what is also very interesting here, this red bar indicates an experiment that claims to see a hint for a sterile neutrino. So we are touching upon this hint, but we cannot yet check if it's right. We cannot yet exclude it. In the future, we will, this is your projection for the future. So you see that we will be able to probe a large fraction of the preferred reactor anomaly parameter space. And this really nicely shows the complementarity of the oscillation and beta decay searches for sterile neutrinos. Now going to the other type of sterile neutrino, the bit heavier, the KeV scale sterile neutrinos. In this case, obviously, the signal appears much further away from the endpoint, because now the force mass eigenstate takes kilo electron volts away from the beta electron. And the big challenge here is that the amplitude of this signal is expected to be extremely small. And from a technical point of view, the rates of beta electrons will be much, much higher if you go deeper into the spectrum. So currently, CATRIN is designed to measure very low rates close to the endpoint. But if we want to look for such a signal, the system is simply not made for that. So I will go a little bit quickly here just to give you an impression. So here you see indirect searches for the sterile neutrino, and you see that they essentially exclude parameter space at the level of 10 to the minus 7 mixing angle. However, all these bounds are rather model dependent, and there was recently a very interesting publication from scientists at the MPIK that showed that these can also be different if you consider some model modifications. There is essentially no laboratory limit that currently competes with these indirect searches. And CATRIN, just from a statistical point of view, using the tritium source that is currently available, could improve these laboratory limits by several orders of magnitudes, and potentially even reach into some region that then becomes interesting from this cosmological point of view. Of course, the challenge are systematic uncertainties, and here we did various studies to show that as long as we have to deal with smooth corrections to the spectrum, the sensitivity is not reduced so much. So the key point, without going into detail, is that the sterile neutrino leaves a characteristic signature, and this is the smoking gun, and we are looking really for this kink in the spectrum. So we already tried that. So we performed a proof of principle with the first commissioning data of CATRIN. And here we had a low activity of tritium, and this allowed us to look deeper into the spectrum without destroying the detector. So we could lower the retarding potential, and the amount of electrons reaching the detector was low enough that the detector could handle the count rates. You can see here the neutrino mass region, and we extend this quite a lot. And the very promising result here was that we still find an excellent agreement of our model with the data. So this is, of course, the prerequisite for such a measurement. And here we reach already mixing angles at the level of 10 to the minus 3, which already improves with respect to previous laboratory searches. But of course, we want to go further. We want to perform a high statistic search for sterile neutrinos using the full CATRIN source strength. And our goal is to reach at the ppm level. So this is very challenging, but we are trying and to see if this is feasible. So considering here the tritium source with 10 to the 11 decays per second, if you would just measure all these electrons, you would end up with a signal rate of 10 to the 10 electrons per second. These are rates like at the LHC. So you need a new advanced detector in order to handle these count rates, and probably we will also reduce the activity a little bit to loosen the requirements for the detector a little bit. This new detector should not only count electrons, but it should also measure the energy of the electrons. We think that by combining the integral and the differential measurement of the spectrum, which are prone to completely different systematic uncertainties, we get a better handle on avoiding false positive signals. So this detector has to be able to handle high count rates, as I said, and we want it to have a good energy resolution. And for these reasons, we decided for the silicon drift detector technology. And this is the proven technology shown here. So it features this small readout contact, which leads to a small capacity of the detector. And therefore, we can have a large detector operating at high rates and still give a very low noise level. So this is typically used for X-rays, but the novelty here is that we want to use it for beta spectroscopy. And as shown here, we want to build a large array of that of 20 centimeters. And this also has never been done before, such a large surface of silicon drift detectors. To do that, we have started a Tristan team. So this detector is called Tristan, and my group is leading this project. Of course, many catering institutions are participating, and a very important partner is the semiconductor lab of the Max Planck Society, which is actually building these silicon drift detectors for us. And then we have some partners in Italy and the US. We go in a staged approach, starting with a prototype, then building a module, which is one unit of the full system, and the final system will then consist of 21 of these modules. So this prototype we have investigated very detailed, first with X-rays, and here you can really see the nice performance. So it has a beautiful energy resolution close to the Fano limit for silicon detectors, a very good noise performance, which is shown here. You can see that we get good energy resolution at small peaking times, which is needed for higher rate applications. And also the linearity is extremely good. Of course, these are X-rays, and we are actually interested in the electron response of these detectors. And that's not obvious how to test that. So we had to find electron calibration sources, and here we used, in fact, an electron microscope at the HLL, not to observe the surface, but to use these electrons as a source of electrons, to measure them with the detector. And the krypton source, krypton, as you have heard before, is also used in the Catron experiment. We use a solid krypton source. The difference for the electrons is that they have a high probability to backscatter on the surface and only deposit a little bit of energy. And also they deposit energy immediately as they enter the detector. And in these first few nanometers, the detector is not sensitive to charge deposition. So inevitably, we will lose some of the electrons' energy in this so-called dead layer. So these are the two challenges. And we have investigated that with these two sources. And here you see a spectrum of a monoenergetic electron. First of all, you see that resolution is still relatively good at 300 electron volt. It fulfills the requirement. And more importantly, we have a good description of the overall shape. So the main peak, then some tail due to the dead layer, and here is the backscattering contribution. We were also able to determine the thickness of the dead layer by tilting the detector and thereby effectively increasing or decreasing the thickness. And through comparison with simulation, we could determine that the dead layer is less than 50 nanometers, which is extremely good for this type of detector. Of course, the question is, how precisely do we have to know all these parameters? And this was done with a Monte Carlo study. And I will only explain you this graph because I think I'm running a bit late. So here you can see the dead layer of 10 or 50 nanometers, and we assume a certain uncertainty on this parameter. And you can see that the sensitivity is reduced, but not too drastically. So actually a reasonable uncertainty on this parameter is okay to not ruin the overall sensitivity of the experiment. And if electrons can be post-accelerated onto the detector, so boosted in energy, actually, we can very much mitigate this effect. This detector was not only characterized, but also used for sterile neutrino search. And this was quite a fun project where we brought the detector actually to Russia, to the old Troitsk experiment. And in this experiment, were able to perform both a differential and an integral measurement. And here you can see the nice results from this campaign. The detector also is already implemented in the Katrine beamline. You maybe remember from one of the first slides, it serves as an activity monitor for Katrine. So it monitors the beta activity, and of course at the same time we see a nice differential tritium spectrum, which we can use as a test bench to actually learn how to analyze such a tritium spectrum. So this first prototype was quite successful, and now we are going for the module. The module has now 166 pixels, and the characterization of this device is currently ongoing. So you can see here a graph of this photograph of this module, and it's quite a high-tech device, I would say. So here is the holding and cooling structure. And here is a very expensive material, silicon carbide, which is used as a cooling link. And then here on front, you have this focal plane of silicon drift detector. And this, the key point here is that it now has an integrated FET. And that means the amplification takes place already in the detector. And that allows us to put the front-end electronics further away from the detector, essentially behind the detector. So this integrated JFET design allows for this 3D configuration of the detector. Here is a rigid flex PCB, also quite a complicated piece of hardware. And here comes then the far away front end electronics. This is a custom designed ASIC that we call Ettore. So this new detector with the integrated FET was tested first again on a small scale. You can see here the ASIC, which is in quite some distance. And we could show a good performance, again, good linearity and good energy resolution. Now we are scaling up. So this was only 7 pixels, but eventually we want to come to the 166. And here again, we follow a staged approach. So you can see here, we start with something 2D, which is always easier than 3-dimensional configuration. So 2D, then 3D, but less pixels. And then we come to the final module. And here, this is a very recent picture, and we are extremely proud that these 48, in fact, it's 47 pixels, they all work nicely. We see a nice spectrum in all of them, and the resolution is below 300 electron volt full width half max in all detectors. And that means that this system is ready to be integrated at KIT. And this is what is happening right now as I'm speaking. So the idea is that we take this module and actually integrate it into the old MINDS experiment. So MINDS is the predecessor of Katrine, and here you see a technical drawing of this experiment. And the old MINDS experiment is in fact now located at KIT, and it functions as a high voltage monitoring device. The good thing for Tristan is that it is a MAC-E filter, so we can test our detector in exactly the interesting conditions. So in low vacuum with a high magnetic field, and we have all the situation just like in the final Katrine experiment. The experiment has also a krypton calibration source, and we are considering even to use a solid tritium source to already perform sterile neutrino searches. And so here, if you look at this technical drawing, you see here the module installed on a long stick. And if I go to the next slide, you see how it is then with these jigs inserted into the magnet. These pictures, they are from essentially yesterday or the day before. So a group from the Max Planck Institute is currently here in the laboratory where the spectrometer sits. And all of this is assembled, and here you can see how it is pushed into the vacuum. And so I didn't put it in, but last night I received the first spectrum taken with the detector with a closed system in the spectrometer. So this is not yet optimized, so I didn't put it here. But in fact, after this talk, just in an hour or so, I will drive to KIT and meet the crew there to see what they have achieved. So then, once this is done, so this will be this year, we then consider, of course, the final system, and the building of the final system is also supported by an ERC starting grant. And here the idea is to first go to 9 modules. So this will be a smaller version, which is good because it fits into the existing Catrine detector chamber. So it is simpler, and we will start with this. And the two big things that we still have to do is we want to develop a new DAQ system, and the modeling of the spectrum is still something that needs some work. So prospectively, we will be able to integrate this after the neutrino mass measurement in 2024 or 2025. Here you can see a nice mechanical mock-up of these 9 systems, how it could eventually look like. So besides these application in the Catrine experiment to search for sterile neutrinos, it turns out that the STD technology is quite interesting for various fields in astroparticle physics or also space science. And here we started some spin-offs. So for example, the Tristan detector, we are investigating if we can use that in a CUBE satellite mission, where it would observe the polarization of X-rays from the Cygnus X1 object. And on the other hand, we are considering to use the Tristan detector as an X-ray detector in this next generation solar axion experiment, YAXO. Here also a very impressive instrument. You can see here a person. And here it would be ideally suited to detect the X-rays that are produced when axions are converted to photons. So these are kind of interesting spin-offs that we are also quite excited about. All right, so that brings me to my conclusion. With Catrine, with the first measurement of Catrine, we were able to set a new world best limit on the neutrino mass based on a direct measurement of about 1 electron volt. With the upcoming 1000 days of data taking, we will then tackle the low sub-electron volt sensitivity. With this data set, we have been able to set some first constraints on light sterile neutrinos. And we could show that there is quite some promising potential to also look for a heavier version of the sterile neutrinos, these KeV scale sterile neutrinos. And in this context, we are building a new detector, and there is quite some progress in the R&D towards this large-scale silicon drift detector focal plane array. So with that, I would like to thank you for your attention, and I'm happy to get some questions.